Okay. It's been there for several years, but that's okay. All right. So we are wrapping up thermochemistry. And if you remember, we had, this is how I thought of it, we had this energy scale, and we have these states of matter. Which one's at the bottom? Solid, liquid, gas. Yeah. Okay. So that means if you're going up, what's the sign of Q? Positive. If you're going down, Q would be negative. Good. Okay. We have some terminology we need to get down here. If I talked about going, so we're talking about enthalpy change, enthalpy of vaporization. In general, TRS probably stands for transition. Okay, let's see if we recognize some of these. If you go from solid to liquid, or liquid to solid, since we already have the sign down, what do we call that delta H? What was the little, what was it? They didn't say melting, just to give you a hint. It was fusion. Okay, then you had liquid to gas, or gas to liquid. VAP, vaporization. How about jumping from solid to gas? Sublimation. Ooh, someone remembers something. Sublimation. Right. Okay. So that's going either way. Right? Gas to solid or solid to gas. Okay. So you look those up for different compounds, and now that we know how to handle Q, we're good to go for that. Enthalpy of a reaction. Let's say I have a reaction. I have little a, big A, right? Little b, big B. So big A and big B are my compounds, and little letters are my stoichiometric coefficients. Right? And then you get usually we just said delta H. But it's a reaction, so now they're just slapping on a little r. Okay. And let's pretend it is positive 300 kilojoules per mole. Oh, no, don't they just say kilojoules? No, they do say per mole, right? Okay. If I had, I don't know, in that reaction, this is where things get confusing. If I had a mole of C, right, or gram, usually they say so many, C is some product, ethane, right? And so many grams of ethane were produced. You know, what's the enthalpy of the reaction? Those types of questions. Remember that kind of thing? Okay, so many grams of C. Well, first you convert it into moles of C, and then you use this conversion factor to get it into heat. And heat has what units? Kilojoules. The trick is that's 300 kilojoules per what? Per mole, but you have a little c in front of the c. Think of it as a 3, I don't know. What would be your conversion factor? Right? You had the grams of C, you converted it into moles of C, and then you had to convert it into kilojoules. But what's the conversion factor? It's right here. 300 kilojoules for... You have to go by the reaction. So it's going to be 300 kilojoules for every 3 moles of C. 300 kilojoules for every little b moles of B. 300 kilojoules positive for every little a moles of A. So you have to go by the reaction. And since it is that way, you can avoid some trouble just by, let's put back our little c to make this work for anything. Before you mess with anything, just divide through by little c. And then you're back to doing things how you're used to doing them, right? Because then you can't screw up because it's a 1 in front of the c. Oh, got to divide this guy by c though too, right? Okay. But I don't think you need to worry about it. I would just realize that if they give you a reaction, just realize it's kilojoules. That's why I kind of don't like write. I was hesitant to write this, but I think the book does. Everybody does. I like writing it this way because then it's 300 kilojoules for every C moles of C, or 300 kilojoules for every B moles of B, right? I like it better that way, but they don't. The convention is to write an MOL there, which is kind of misleading.
You have a degree sign by the delta RH.
Oh, what does that mean?
Because it's supposed to actually be a little thing coming through.
Sometimes they do this.
Because that's what you have.
Sometimes they do that, yeah. Yeah. What is that? That or this? It's not degrees. It means it's in the book, it's in the tables, it's standard states. All right? And we're going to get into standard state isn't really that straightforward anymore. And we're going to see that. Usually we'd say it's, 1 atmosphere, 25 degrees Celsius. No. We're going to find out that that's not really the case. Okay. Stoichiometric numbers. Those are just what? My little a, little b, little c. Okay. And they're going to come into play here in a little bit. Okay. We need to be able to write combustion reactions. And the only thing you got to remember is what do you produce? You burn something, what's going to definitely react? Whatever you're burning, like some organic compound, but it reacts with what? O2 in what state? Gas. Then it always forms what and what? CO2 and water. But you got to know the state. CO2 is a gas. The water has to be liquid. Remember that. You're going to form CO2 gas and H2O liquid, right, when you start writing this stuff. All right, those that, and, whoop. Now you're going to have stoichiometric coefficients in front of this stuff, right, to balance it. And you're going to have such a number over here. This is where the convention, I think, gets confusing. Enthalpy of combustion. We're going to, I think, hit on that later and further down in the outline, but you want to rearrange this equation. Enthalpy of combustion of propane, right? So you're going to have propane over here. But you want there to be a stoichiometric coefficient of what in front of propane? You want it to be a 1. Because the talk is the enthalpy of combustion of propane. So they're really talking about this delta HC, that's per mole of whatever they're talking about burning. So when you rearrange this thing, if you have to multiply that compound you're burning times 2 or 3 to whatever to get things to balance, just make sure you divide through by it to get a 1 in front of it. Okay? It has to be a liquid. Big deal. Has to. Doesn't matter what you're burning. That's the convention. Enthalpy of combustion is always CO2 gas and water liquid. Yeah, remember that. Otherwise, that'll really bite you in a little bit. Okay. Hess's law. We talked about that. Madison, what did we say this Hess's law was? Right? Oh, might as well, instead of saying delta H of some reaction, I guess we stick with delta RH. They like to have a little R in there. What's one way to get it? Here's some hints. Right? And you know the delta H for all these little guys? Yeah, you can, if you add up a bunch of reactions and you know their delta H, whatever you add up and get, add up all the delta H's and you'll have your answer, right? That's Hess's law. Okay. So, and what they're trying to say is enthalpy a state function? kind of a vague question, but it's there if you think about it. If it's a state function, is it path dependent? Or just final initial states matter? Just final initial states matter. It doesn't matter how you get there. It's not path dependent. So, because you can use Hess's law and add up different reactions, as long as you get the same final reaction, you can get the same delta RH, the same enthalpy for that reaction. So enthalpy is a state function. And that's why Hess's law works in the first place, is because enthalpy is a state function. So it doesn't matter how you get there. It doesn't matter what reactions you use. As long as everything adds up and cancels out to get the overall reaction, the same overall reaction, you get the same enthalpy for that reaction using Hess's law. Okay. Okay, enthalpy of formation. Now again, they have that little superscript 0. So that means we're going to be using what? Standard states are going to be using tables, right? Because standard states. And when you look that up for a compound, what does that look like? For example, let's pick one. CH3OH liquid. I could have I could have methanol gas, I could have methanol solid, methanol. It doesn't really matter. You're just going to look up a different enthalpy of formation for it, right? That makes everybody with me so far? You can look up these numbers. Methanol liquid, methanol solid, methanol gas. They're going to have a different enthalpy of formation. But we need to be able to write the reaction that gives us that product. Okay. Now the hint is that it's formation, so that means whatever it's enthalpy of formation of, that compound's got to be the product. All right, if we're going to write one of these. But what are the reactants? What's that? That's for enthalpy of combustion reaction, and those carbon dioxide and water are products. Here's a hint. I don't know if it's much of a hint. Reference state. Oh, okay, OH maybe. Is OH, I don't know if this is much of a hint, is OH the reference state of O and H? All right. Reference state, enthalpy of combustion, is all the reactants in their reference state form this product. So you have to think of carbon in its reference state. You have to think of hydrogen in its the element carbon in its reference state.
So solid carbon, hydrogen gas.
Okay, well we're getting there. And oxygen in its reference state. Now what are these reference states? This is where I mentioned that, and you're getting there, Rob. You're getting there, or you probably are there. But the point is you'd think we could say 1 atmosphere, 25 degrees Celsius all the time. No, you can't. So if it's a gas, what's the reference state? Well, it's 1 bar, right? If it's a solution, a mixture of sodium chloride or something, it has to be 1 molar and 1 bar pressure. If it's, who are my analytical people? Who's an analytical right now? Kathleen's, right? Analytical. If it's a solid or a liquid, what's the reference state? If it's a pure solid or a pure liquid, the reference state is pure solid or the pure liquid. Remember, they're going to end up canceling. We talked about that in analytical. In a different terminology, though, but it's the same thing. It's going to be the pure solid or the pure liquid. So nothing really changes. Same thing. Pure solid or the pure liquid. The funky one, I think, is if it's an element. If it's an element, right? It needs to be its most stable form. That's not the best. I guess that's the best way to say it, right? So, but what changes, it has to be 1 bar. And the temperature, whatever temperature gives it its most stable form. So it's not always 25 degrees Celsius. So and the temperature, that gives most stable form or something. So it's a long answer to help you decide what this is. You have to have carbon in its reference state, hydrogen in its reference state, oxygen in its reference state. So carbon in its reference state would be what, probably? Its most stable form would probably just be carbon solid. Oxygen in its reference state would be, O gas, but O2 gas. And the same with the hydrogen, right? And then we got to balance it. How would you balance it? How would you balance it? Put a 2 in front of the hydrogen. Oh, it is 4. Shoot. I picked out a bad one. Okay. I was hoping that we would have to mess with the methanol to get this thing to balance. Okay, we can't. Well, we can help. Okay, so we multiply everything through by 2. If you really want to follow convention, you'd have a 2 in front of here, 1 in front of the oxygen, 4 in front of the hydrogen, a 2 in front of the methanol. Okay. So, do they like this 2 there or not? Does everybody agree it's going to look like this? Does everybody agree? Okay. Everybody agrees so far, right? Everyone's with me? You look up the enthalpy of formation of methanol liquid. Are they assuming you're talking about this reaction? Because remember, it really matters what the reaction is. Because it's always per mole. Is it this reaction? Well, yeah, we have a liquid there. So you look up the enthalpy formation of methanol liquid. It's some number, 712 kilojoules per mole. Does it refer to this? This is where things are kind of, they assume that you realize this. You always have to have a what in front of the compound. It always has to be a 1. Doesn't matter what your balanced chemical equation is. You have to have a 1 in front of that compound that you just looked up in the table. If you look up methanol liquid, it's negative 238. So that's negative 238 kilojoules per 1 mole of this. And that's key. So that means we got to divide. We had it right the first time, is what I'm saying. You don't mess with it. If you have a 1 in front of that enthalpy, whatever the enthalpy formation is, that compound has to have a 1 in front. It has to. That's their convention. Okay. That's their convention. Okay. So combining enthalpies of formation to get an enthalpy of a reaction. Does that look familiar? Combining enthalpies of formation to get the enthalpy of a reaction. I think it's one way to look at Hess's law. I don't know, I guess it should work at Hess's law. I never worked it out. But this is when you did what? You had a reaction, and you looked up the what for everything to get the overall enthalpy of the reaction. You added all these up for the products. You added them all up for the reactants. You subtracted them, and you got your answer. Enthalpy of formation. That's all this is saying, right? add up all the enthalpies of formation for the products. Add up all the enthalpies of formation for the reactants. And subtract them. Now what is this little new symbol then? What is that? It's because it's what it's saying is multiply that new symbol times the enthalpy of formation, the standard enthalpy of formation. Oh, they're trying to make it general. This is going to work for enthalpies of a reaction. It's going to work for, it's the only one I can imagine, but it's going to work for everything with these tables. What's the little new symbol? Yeah, it's a stoichiometric number. It's a stoichiometric coefficient. And we know that. That's what we did. If we have multiply the stoichiometric coefficients times enthalpies of formation, right? Add them all up for the products, add them all up for the reactants, and subtract the two. Okay. It just looks kind of funky there, but that's what they're doing. Okay. Let's help us prep. Let's do. Let's burn. I'm just trying to see if you remember your organic. Pentane. Pentane means 5, right? Okay, so it's C5H what? What was the rule for this? Times 2 plus 2. C5H12. Okay, let's write the enthalpy of combustion for pentane. How would you do this? Oh, and you should probably say that pentane gas is a pentane liquid. Let's say it's pentane gas. So how would you do this? All right, you're always going to get what and what? And carbon dioxide in what state? Gas. And you're going to get in a liquid. Okay. Now we need to balance it. So we'll probably have to put a what in front of the CO2, it looks like. Oh, we forgot our oxygen. We're going to need that, right? It's not going to go very far. Okay. See oxygen's everywhere? Don't balance it first. Balance the carbons first, or the hydrogens. Carbons, you got how many? 5, so put a 5 in front of here. All right, now the hydrogens. I've got 12, so I can put a what here maybe and see if it works. Put a 6. Oh, please work, right? 5 times 2 is 10, plus 6 is 16. Oh, so put a what here? An 8. Okay. If you had to put a fraction, fine. Put a fraction here, right? If you needed 9 oxygens on this side, if you needed, just pretend, you did 9 oxygens on the product side, what would you put in front of the O2? There's nothing here with the pentane, so what would you put in front of the O2? You need 9. Cheat. Put a 9 over 2 and leave it there because you need to have a 1 in front of this thing, right? It's enthalpy of combustion of pentane, so they're assuming it's a 1. So if you need a 9, you don't have to put 9 over 2 and leave it there. Okay. So you can get enthalpy of combustion out of that. There's one thing that the homework is going to start messing with, though, and that's because let's start at the beginning. Erase delta H. Well, H equals U plus PV. All right. So delta H equals delta U plus delta PV. Okay. And talking about reactions, let's put a little R on stuff. Okay. And that's supposed to say PV. Do you recognize that?
Yeah.
Okay. So delta RH, see where this is coming from. Delta RH, forgot my, equals delta, the reaction change for the internal energy, plus. Now PV is really just nRT. It's going to be a lot easier to mess with than pressure and volume. So keep the temperature the constant you're going to have delta N. Okay. So for the PV, I put in nRT. And what they're getting at is that this is supposed to be work here. And this is the energy from my work and how it's affecting the enthalpy. And all they're really interested in is what work can it do? It can either push against the atmosphere or the atmosphere can push against it. And if you're not, the only way for it to push against the atmosphere in these types of things is if you're generating gas. You have to generate some gas molecules. Change the number of moles of gas. And that's why the book has a little g down here to be more specific and say, okay, the enthalpy of a reaction, R's in the wrong place. Enthalpy of a reaction is the change in internal energy of the system plus, okay, well, let's mess with some work here. If you don't change the number of gas molecules, then forget it. Don't worry about it. And to get the delta N, where are the moles here? Aren't they the, what do you call these things out front? Stoichiometric coefficients. Those are the moles. So what is my delta Ng for that reaction? You see it? What would it be? Final minus initial. So the total gas on the product side is 5. Total over here is 9. So my delta Ng is -4, right? Okay. I wonder if they have that negative in there. I don't remember. I think that's right. Okay. And then you can find the enthalpy of a reaction at different temperatures. Right? Because T2 is your new temperature. T1 is some temperature you're starting out at. So they must tell you an enthalpy of a reaction at some temperature. Right? And then how do you get the enthalpy of a reaction at a new temperature? Well, add up that enthalpy of reaction at the temperature you know plus T2 minus T1. That's just another way of writing delta T, the change in temperature, times this funky thing, delta R Cp 0. Standard change in heat capacity, I guess, constant pressure. Well, how do you find it? You have to find using this equation. And what's nice is they're being consistent, I think. Right? To use that equation, it looks like it's some summation over J. What's this new J? They're trying to be consistent. Stoichiometric coefficients. Except they're, that compound J. Stoichiometric coefficients of that compound J. So you have to look up the molar heat capacity at constant pressure for all this stuff, multiplying by their stoichiometric coefficients. But one thing that is not quite clear in this equation is that no, they're just saying compound J. Counters, I like counters as I better, but that's okay. They use big J. Notice that symbol is new. How do you write new? That guy? Does he have a different sign for products and reactants? Right? Because you did products minus reactants. And for reactants, that little symbol, stoichiometric coefficients, are really all negative. And this is where the book kind of, I don't think did a very good job. They should have stayed in the same format for this relationship as they did down here. They're trying to say this little nu j is my stoichiometric coefficients, but it's positive for products and it's negative for reactants. I wish they would have been consistent, but they're not. I don't know. It's not too many places the book kind of screws up, but they did there, I think. That nu j, there's a rule for it. It's a stoichiometric coefficients, and it's positive for products and negative for reactants. Okay, so here's some questions. Yes? Formal equation? I think they're talking about, I hope what they're talking about is this argument we were saying here about how enthalpy for a reaction is per mole, and it really corresponds with the reaction. But they're saying formal equation because enthalpy of formation, you can't just write any reaction you want. If you're talking about the enthalpy of formation of methanol gas, there has to be a stoichiometric coefficient of what in front of methanol gas in that enthalpy of formation reaction. It has to be a 1. I think that's what they're saying with formal equation. You can't just write any equation you want and balance it. You have to have a 1 in front of what you're interested in. Enthalpy of combustion, you got to have a 1 in front of whatever you're burning, whatever you're combusting. Enthalpy of formation, you got to have a 1 in front of whatever you're interested in looking up in that table. Enthalpy of formation of what? Propane. Well, it needs to have a 1 in front of the propane then in the reaction, if you're going to write it. Okay. That's what I hope they're talking about for formal reaction. Oh, we don't need that. It's all right here. Okay. A certain liquid. So any other questions before we do this? A certain liquid has enthalpy of vaporization, standard enthalpy of vaporization, 26 kilojoules per mole. Find Q, W, delta H, delta U. 5 moles is 0.5 moles is vaporized. 250 Kelvin, 750 torr. Any ideas? Well, yeah, we can jump at the equation sheet. But right away, when I see enthalpy, you know your Q. You're going to be using that to get your Q. And you can use the equation sheet for it. But if they give you the enthalpy, that's all what enthalpy is talking about is Q. Except Q doesn't want to have a per mole in it. Q just wants the kilojoules. So I don't think the equation sheet's going to help you to find Q. Well, what could you do to find your Q? Yeah, multiply the enthalpy in the moles. Because look at the units. Right? So there isn't really an equation for it. So the enthalpy to vaporize 0.5 moles, all right, you just use the enthalpy of vaporization to get it. I guess if you wanted an equation, you could write it times the number of moles, but I think the equation itself is given by the units. Now we have to slap on the sign. So that's 13, right? Do we put on a positive or a negative sign on that? Because that's the part you got to remember, I think. We're going from what to what? Liquid to gas, so we're going up the ladder. It's got to be positive. You're going up the ladder. You should write positive just to emphasize the fact, I think. But if you don't write a sign, it has to mean it infers positive. Okay. That's our Q. What other one can we hunt for? For W? For W, oh, how about, hey, they asked for delta H. Is Q the same as our delta H? Yeah. Because, well, I guess we don't know for sure, but pressure's constant, so. If they would have, I wish they would have said it. Then it would be as clear as day. Does it have the same sign? Yeah. Okay, we've got that one. So we've got our Q, we got our delta H. What always holds for delta U? Change in internal energy. It's always Q plus W. So we got to find W. Yeah, that doesn't really help. Well, find W and we'll have it. Doesn't work what?
Doesn't work in units of
Yeah, work is units of joules for sure.
Could you do the delta H half times 0.5 moles?
Okay, if you do delta VAP H times the 0.5 moles, like we did to get Q, that's Q. Q and W aren't the same thing, right? W you have to think of, I almost have to think of, okay, what the hell's going on here?
Pressure.
Is,
Yeah, it's pressure.
okay, we could do the U plus PV, but you're kind of going chasing your tail. You don't know what U is, and yeah, we know what H is, we don't know what U is. Think of work. What relationships did we have for work? And how could this thing be doing work? It's vaporizing. It's turning from a liquid to a gas. So to do that, does it have to push the atmosphere out of the way? If it's turning into a gas, you're generating a gas. It needs to take up some more space. It's changing volume. So if it's, yeah, I think that's what you got to think of. That the darn thing's changing volume. If it's changing volume, there's work, PV work, because all we're ever talking about are gases. Except here we kind of have a liquid, but it's changing volume, so you're going to have work. It's weird to think of expansion as work, but it is. Things expand, they're gonna cool down because it takes energy to do it. You have to push that atmosphere out of the way. I mean, it's just, if we lived in a vacuum, we'd be okay. But so this PV work is really the only type of work we have to work with, and that's PV work's the only type of work we have. Anyway, you only had two types. It's either reversible or irreversible, right? And it goes back to what we had before. If you use the irreversible relationship, you know, you remember messing with the natural log at 0 and stuff, but we got the same answer if we just assumed it was irreversible. What was the equation for that? Negative PEX times a change in volume. So change in volume is VF minus VI, right? Because they didn't give us really jack here. Now which one, well, we probably will. Which one, what is this? This is the volume of a what? That's a volume of a what? Liquid and a gas. Which one's the liquid? The initial is the liquid. So that's our liquid. And this is our gas. Can we say that one is a lot bigger than the other one? Is that how nature works? You take a drop of liquid, convert it into a gas. So the drop had that extremely small volume, convert it into a gas, and fill up the whole container. So volume of a gas is always a lot bigger, right? So you could say And what was the way to write that? You could write greater than, but it'd look better if you wrote two greater thans, remember? VF is much, much, much bigger than VI. Okay? So this is really minus PX V. And we could find P and V, but it might be easier to recognize PV is really just an RT. So you can go, I think you can, I think it's easier just to put an NRT for it. Because you know what V, you know what PV is. You don't really know what P or V is, but you know the multiply the two, you get NRT. So that's how we're going to get our work. And once you get your work, you can get delta U. Okay? Are we okay with it? Calculate the standard enthalpy of hydrogenation of 1 hexene to 1 hexane. Now, if you're not sure what hydrogenation is, the big hint is hexene to hexane. What's hydrogenation? What's actually happening? We're adding, not water, but hydrogen, right? Because it's going from a double bond to a single bond. So you're just adding hydrogen. So what they want to know, what's the standard enthalpy of hydrogenation? So they want to know what's this reaction of what? Let's write the reaction that they're after. Standard enthalpy of hydrogenation of 1 hexene to 1 hexane. Now hexane, that one I can write. That's C6H14. Okay? They didn't say anything, so I'm going to say it's a gas. All right? What's hexene? C6H12. Gas. All right. Enthalpy of hydrogenation. So I'm missing a reactant. Hydrogen. H2. Okay. This is what they want to know. They want to know the enthalpy for that reaction. You with me so far? Did I lose you? Okay. Given that, this is one of those game plans where you have to write out all these different reactions and add them up to get to this one. All right, so we're going to write out some reactions, and we're going to rearrange them so that when we add them up, we'll get the reaction we're after. We'll add up their delta H's too to get it. So they're saying that given that, here's where we start writing reactions. The standard enthalpy of combustion of 1 hexene is, so we have negative 4,300 kilojoules. For what reaction? So this is the one we want to find. Let's write out this first reaction. How would you write the enthalpy of combustion of 1 hexene? O2 gas, keep going, plus the hexene, and we're just pretending it's a gas. I don't think it matters. Again, it's going to give H2O liquid and CO2 gas. Right. Okay. Now we don't have enough here. But here's our first reaction. Do we need to flip them or anything? Do we leave them alone? We're going to have to write more reactions, and we may not have a clue where they're coming from, but we'll get them. So when is this first top reaction, is he okay where he is? Or do we need to multiply by 2, or what's the only thing I can look at is what? The hexene. Look at that hexene. Is he on the side you want him on? Yeah. Right? You add up this reaction to who knows what. Hexene is right. You have the right stoichiometric coefficient in front of hexene. Yeah, it's a 1. And it's a 1 up on top. So don't mess with that top reaction. Don't flip it. Don't multiply by anything. Nothing. Leave him alone. Okay? Makes sense so far? So what are these other reactions? These other reactions, where is our enthalpy of formation stuff? Page 922? Oh, yeah. There's a bunch. Where does it start? Oh, you're right. It starts on page 922. Look at all these compounds, and they all have an enthalpy of formation. There's got, I don't know, let's say there's 100 of them. They just gave you 100 reactions and their enthalpy of that reaction. Because we know how to write enthalpy of formation reactions. You write enthalpy of formation of, I don't care, let's pick one. We have to get H2O liquid. We need H2O liquid's enthalpy of formation. Let's write it down here in green or something to show you what I'm driving at here. Right? Because we have to get rid of H2O liquid. If you write enthalpy of formation of H2O liquids, right? First, let's look it up. H2O liquid. Oh gosh, where is it? H2O liquid. Oh, there it is. It's on page 926 at the very top. It's negative 285.83. Negative 285.83. Okay? Kilojoules per mole. So I looked up H2O liquid. You're expected to know how to write its enthalpy of formation reaction. Make sure there's a 1 in front of this guy that you're forming. So he's going to form from his elements in the reference states, H2 gas and O2 gas. Balance it. Put a what? Put a half in front of the O2 and leave it there. Right? Okay. I lost anybody? Okay. So what I'm trying to say is by that table of enthalpies of formations, you have all these reactions. You just have to write them. And you know the enthalpy of that reaction. So you've got a gazillion of these things to play this game with. And the reason why I wrote H2O liquid is because I saw it there. Okay. So here's our reaction. What do we need to do? Do we want H2O liquid in our final answer? No, so we better get them to cancel. So what should we do to this reaction? Flip them. Do we multiply by anything? Let this guide you. Do we multiply by anything? Well, I'm just saying this guy, we want only 1 to cancel. So just looking at the H2O liquid, don't multiply this through by anything because you just want 1 H2O liquid to cancel, otherwise you're going to mess it up.
Yeah, that's not balanced.
We didn't balance them?
No.
Oh, we skipped that step, didn't we? Okay.
You said leave it alone, so.
We better balance them. How do you balance this thing? Okay, 6 carbons, 6 there. Okay. How many waters? Should be 6, right? Okay, so 6 and 12 is 18, so that'd be a 9 over here. Oh, that makes a huge difference, doesn't it? Right? Okay, so now we want 6 waters over on this side, right? So we're going to flip this reaction. Not only flip it, but multiply it through by 6. Good, I'm glad you noticed that, because I didn't even see it. Okay, so multiply through by 6. So we're going to have 6 hydrogens then. And how many oxygens? 3 of them. And what are we going to write as our delta H? Positive 285.83, close, Finish it. Yeah, but you multiply through by 6. Times 6. Whatever you do to that equation, you got to keep those ratios all the same. So if you multiply through by 6, you got to multiply him by 6. If you divide by 2, you got to divide the delta H by 2. Okay, if we add everything up now, will we get what we want? Or is something still missing? The carbon dioxide. You're going to have to look up the enthalpy formation of carbon dioxide, gas or liquid? Gas. And it looks to me like you're going to have to flip it. And multiply through by 6. And you're going to write that one here. And you're going to add everything up, make sure you get the top reaction.
Okay.
And
We have the hexene, but we're leaving out the hexane in the whole thing. So
we're going to need, we're going to need another reaction then. We're going to need the enthalpy of formation of hex, because we already have hexene. We need the enthalpy of formation of hexane. So we're going to need it. We better erase that. We need another reaction in here. So you're going to need 2. So you're going to have,
will we need another reaction?
because otherwise hexane
Hexane
doesn't show up.
Because if we do what we did with the hexene to the hexane, we'll have water and carbon in there.
It'll work out.
The water?
It'll work out. Because when you do the enthalpy of formation of hexene, water's not going to be in there. Because our water's already taken care of. Enthalpy of formation of carbon dioxide, water's not there. So we're not going to mess up. The waters are taken care of. We're done with those. So I wouldn't worry about the intermediate guys like the water and that stuff, because they'll take care of themselves. I would just worry about the big dudes. The big dudes are these guys. Everything else will take care of itself. You just kind of got to keep an eye on it. So you're going to write the enthalpy of formation of carbon dioxide, flip it, multiply it by 6, enthalpy of formation of hexane, and don't flip it or anything. Don't even multiply through by anything, because it's just C6H14. Okay? So come by. I'll be glad to help you out on this.